Okay, we continue to learn chapter 3, vector spaces, and section 1, definition and examples. Now we learn part 2, vector spaces, more examples and properties. So first, let V be a set of elements called vectors, on which the operations of addition and scalar multiplication are defined. First, the vectors should satisfy Closure properties on C1, C2. C1 means that if X belongs to this set and alpha is a scalar, then alpha times X also belongs to this set. And the second closure property requires that if X and Y belong to this set, then X plus Y also in this set. So these are two closure properties. And the set V, together with the operations of addition and scalar multiplication, is said to be a vector space, is said to form a vector space if the following axioms are satisfied. We have 8 axioms. The first one, A1, require X plus Y equals Y plus X for any X, Y belongs to V. So this means you can change the positions of the two vectors when doing addition, okay? And A2 requires that if you first compute X plus Y first and then plus Z equals X plus, you first do addition of Y and Z first for any X, Y, Z belongs to this set. And axiom 3 requires that there exists 0 vector in this set such that any X in this set, X plus the 0 vector equals X. And axiom 4 requires that for any X belongs to V, there exists a minus X belongs to V such that X plus a minus X equals 0. So you have an additive inverse of X. Okay, and axiom 5 requires that alpha times the addition of X and Y equals alpha times X plus alpha times Y for any alpha real number and any XY vectors in this set. So they have the distributive property. And also axiom 6, we have alpha plus beta, then times X equals alpha times X plus beta times X for any alpha beta belongs to real number and any X belongs to this set V. And axiom 7 requires that if you first do alpha times beta and then times the vector X, it equals alpha times beta times X first. So we have this property, this axiom for any alpha beta belongs to real number and any X belongs to V. So if the set V together with the two operations satisfy A1 till A8, these 8 axioms, then we say that they form a vector space, or we say they form a linear space. Okay, so to check if a set V together with addition and scalar multiplication forms a vector space, we need to check first if the two addition and scalar multiplication, two operations satisfy the closure property C1 and C2. And then we need to check if it satisfies the 8 axioms. Okay, so you can try to verify that Rn, the n-dimensional real vector space, and Rn by n, this space with n by n matrices, are both vector spaces. So you can show the closure properties for the addition and scalar multiplication. And you can also show these 8 axioms hold for any vectors and the scalar corresponding to these sets. Okay. Now we see an example of a vector space. We write it as CAB. So this CAB denotes the set of all real-valued functions that are defined and continuous on the closed interval AB. So this set contains all the continuous function in the interval a to b, and which are continuous, okay, continuous function in this closed interval a to b. And for these functions, for these vectors in this space, we define f plus g and alpha f by this way. So f plus g function on x equals f function on x plus g function on x. And alpha times f function on x just defined as alpha times f function on x for any x in this closed interval a to b, and for any alpha real number and any f continuous function on ab, okay? And in order to prove that CAB is a vector space, we need to show that the 8 axioms are satisfied. So for example, if we want to show A1 holds, then we check f plus g function on x, if it equals g plus f function on x. Because f plus g function on x just can be written as fx plus gx. And because these are two function values, of course you can change the position. So it equals g of x plus f of x. And g of x plus f of x just can be written as g plus f function on x. Okay, so this is for addition, okay? And if axiom 3 wants you to find a zero vector in this space, in this set, such that any vector in this set plus this zero vector will be itself, this vector itself. And we choose zx equals 0 for all x in a to b. This means we choose the constant function and the value is 0. So this function. And then we check f plus c function on x. As the definition, it equals f of x plus c of x, because c of x just be 0 for any x in the closed interval a to b, so it is just fx. So we know that the zero vector exists in this space, in this set. Okay. Now we see another example for vector space. We write it as Pn. Okay, let Pn denote the set of all polynomials of degree less than n, smaller than n. We define p plus q and alpha times p, the addition and scalar multiplication, in this way. So p plus q function on x equals the polynomial function p of x plus the polynomial function q of x for any x in real number, and any pq belongs to Pn. These are polynomials of degree less than n. And we define the scalar multiplication alpha times p function on x just equals this number alpha times the polynomial function p of x for any x, any alpha, any p belongs to real number, and this set respectively. To prove that this Pn, this set is a vector space, we need to show that the 8 axioms are all satisfied, right? So, for example, if you check A3, you want to find a zero vector in this set, you can just choose it as the zero polynomial. So, g of x equals 0 times x power n minus 1 plus 0 times x n power n minus 2 plus 2 plus 0 times x plus 0. Okay, so you can check all the 8 axioms hold, and addition and scalar multiplication satisfy the closure property. So the addition is also a polynomial function of degree less than n, and also the scalar multiplication, you can show it is also a polynomial function of degree less than n. Okay, now we check some additional properties of vector spaces. So theorem 3.1.1. V is a vector space and X is any element of V. Then we know that the zero number times X times any vector X equals the zero vector in this space. And we also have that X plus Y equals the zero vector implies that Y equals a minus X. That is, the additive of x. So the additive of x is unique. And also, if you use the scalar, the number -1 times x times any vector in this vector space, it is just minus x, the addition, right? The addition inverse of x. Let's prove these properties. Okay, so first we check the first one, the zero vector. Because the zero vector can be written as minus x plus x. This from axiom 4. This is from axiom 4. We have this one, and then because x also equals the number 1 times x according to axiom 8. So we have this one, and 1 times x also equals 1 plus 0 times x, because 1 can be written as 1 plus 0. Okay, and then this from axiom 6, we can get this one equals 1x plus 0 times x. And then we combine the two terms first, which is minus x plus 1x. This from axiom 8.2, right? Axiom 2, we can have this combination plus 0 times x. And from axiom 8, again, we know 1 times x just equals x. Okay, and from axiom 4, we know this one, minus x plus x just equals the zero vector here, and 0 plus 0 times x, we know it's just 0x itself. So the zero vector just equals the scalar 0 times x. So we can show from the definition of a vector space. And the second conclusion, assume that x plus y equals a zero vector, then we know that minus x equals minus x plus the zero vector. Okay, there exists zero vector such that you add this zero vector is itself. And because x plus y equals 0, and you can combine the first two terms together, and this one is just the zero vector. Zero vector plus y equals y itself. And so we know that minus x just equals y. So the additive inverse of x is unique. And the third conclusion is that we can show in this way. Okay, because the zero vector equals 0 times x. We show this already, right? In the first conclusion here, we can use here. 0 equals 0 times x, and the scalar 0 equals 1 plus minus 1. So it is using the distributive property, we can write as 1 times x plus minus 1 times x. And 1 times x using axiom 8, this one is x. So from this equation now, you have minus 1 times x just equals minus x. Okay, so we show these three conclusions. Additional properties of vector spaces. So 0 times x equals 0 vector, x plus y equals 0 implies that y equals minus x, and minus 1, this scalar times x equals the additive inverse of x minus x.